Hello friends, I welcome you all to this session on C++ programming. So as we all are engineers, so we should be in a position to solve some real life problems. And now I'm saying physics problem because that has been derived from fluid mechanics. So now the problem says, it is a very interesting problem friends. It says that let's say two infinitely long plates are there. Infinitely long means not long in this direction but infinitely long into the paper. So the width of the plate is very large. Let me make it better. So this is the one. Now if this is your x-axis and this is your y-axis, then it is given that these two plates are fixed. They are not moving at all. Now fluid enters between these two plates and attain, let's say, laminar flow. Now, due to this, what will happen? A velocity gradient will set up between these two plates. And as we are not going into depth of fluid mechanics, so because of very large extent of the plate in the z direction, that is into the paper, so this becomes an example of a parallel flow where only existing velocity is in this direction, that is x, let's say it is u, and that is the only varying term, velocity, not existing, varying velocity. Others can be kept as a constant. So this will result into two very interesting things, that is u will become function of y, and as this is flow in between one confined passage, so the pressure will also come into picture. The pressure will become function of x. And if you solve the Navier-Stokes equation, that is the fundamental equations for fluid flow, then this will get simply reduced to, as it was non-linear partial differential equation, so that will get converted into ordinary differential equation as d2u by dy2 is 1 by mu dp by dx. As pressure is function of x and u is function of y, so the right hand side for this particular can be taken as a constant. Now, what are the boundary conditions for this ordinary differential equations? If you look closely, when y is equal to 0, or let me write like this, when y is equal to 0, the value of, so when y is equal, again I am writing, when y is equal to 0, the u velocity, that is the x direction velocity, is 0. Yes, why? Because on the boundary, the flow velocity will be equal to the, or the relative velocity between fluid and surface should be 0. And as the surface is at rest, so that should be 0. Similarly, when y becomes h, u will also be 0. Same thing. And that is what in fluid mechanics we call as no slip boundary condition. So, how to solve this differential equation? We will be solving this numerically, that is using Gauss seidel. And if you discretize this in the y direction, considering that the indexes are moving like this, or what you can say is at any cross section you have to take certain number of nodes, let's say equally spaced nodes, okay, and the spacing between them is delta y. So if you are at any ith location, then the value of velocity at that particular location can be evaluated based on the two previous as well as this, or the second derivative. So so it becomes ui plus 1 minus 2 ui plus ui minus 1 by delta y square, and that is equal to 1 by mu dp by dx. So now if you solve this further, so this delta y will be going here, and ui then becomes ui plus 1 plus ui minus 1, okay, and this will come here and then come to the left hand side, so minus delta y square by mu dp by dx, and this whole will be divided by this 2, okay, so it is 1 by 2 of this term. Here you should remember that I already said that dp by dx is what? A constant. Now, if you are wondering that from where this has come, this is nothing but simple what we call as numerical differentiation. Still, if you find it difficult to grasp, then what I'll do is I'll leave a link in the description of this video, so that you can see that particular video of mine where I discuss that how these numerical derivatives comes into picture. Now, what we'll be doing is we will be solving this particular equation between y is equal to 0 to y, if this spacing is h, so y is equal to 0 to this for all the nodes except the boundary nodes. So from the node number 1, if the node starts with 0, as in C, the array starts with 0. So from node number 1 we will be solving, and if this is the total number of nodes are say n, so this will be what? This will be n minus 1th node because it is starting from 0. So I will be solving from 1 to n minus 2, or till the I value is less than n minus 1. Okay. So between these, what I have to do is I have to solve this particular equation iteratively till the solution get converged. So the question is how I will be certain that I have got the correct result. Now, the correct result for this particular one, as this is a very standard problem in fluid mechanics, that is laminar flow. So u as a function of y analytically will be equal to 1 by 2 mu minus dp by dx, and then h minus y times y. Now, here you should remember that mu is the dynamic viscosity of fluid. Dynamic viscosity of fluid. This is the pressure gradient. Obviously, pressure gradient has to be negative because the in the direction of flow, pressure always reduces. So this side, the pressure should be less in comparison to this side. Then only fluid will flow from left to right. Okay. Now this is the task of our basically you can say that this is basically challenge for you, that how to write a class for this. So you can name the class as channel flow. Okay, you can name this class as channel flow, and then to create this you should have some data members. So what should be the data members? So the spacing between the plates, then the dynamic viscosity, that is mu, and the pressure gradient dp by dx. Okay, they all will be our data members. So these have to be supplied. What else? Apart from this, how many nodes you require? So number of nodes, that will also be our input. That means the data member. Apart from this, what else is required basically? Grid spacing. Do we require really grid spacing? No, grid spacing we don't require as such, but we will be evaluating it. So why not to make it data member? Doesn't matter. We will not be supplying it. We will be just evaluating it. Okay. So let us make one more data member, that is delta y or dy. Okay. What else can be the? So as we are solving this numerically, so some tolerance limit has to be there. Some converging criteria has to be there. So let's say that is your epsilon. What else is required? Now, if you look closely, you are evaluating for what? U. So you should have one array of U, isn't it? And as we have to compare it with the exact analytical answer, so we should also have one data member as U exact. Now I think this is all. And one more thing, this U is not going to be an ordinary number. It's not a simple number. It is basically an array. This is also an array, because for every varying y, or varying I, this u will change from 0, 0, and you know how this looks. So basically the velocity profile will be parabolic. It should come parabolic, isn't it? If you look the exact answer here, This is nothing but equation of a parabola, because this is y square term here. So it should be parabolic and the central velocity should be maximum. So the maximum velocity should be at the center. So now friends, this is a challenge for you. In this lecture, I have just explained you the problem. I have also explained that how that can be discretized. Or what I'll do is, okay, I'll give you two more hints. So these are your basically input data or the data members for the class, and then you should be in a position to develop the constructor. So the member functions, they should be what? First the constructor, only make one, that is the parameterized constructor. Then you should be making another function for the boundary condition. Then you should be making one function for solving this particular equation in the domain to get the converged answer, this equation. So let us call that as a solver or simply solve. Okay. So once you have this, that is the constructor, boundary condition, and the solver, means the solve function which will be solving, then you should also have one analytical value or analytical solution. So let's call it as ana solve, or something better name. Oh, let us write analytical solution, doesn't matter. Analytical solution. Okay. And as everything will be done, then after it you should have one function for displaying the result display. You know what, you can also make one array for as though it will not be taking participate in the input data, but you should also have one data member as y, because then only you will be doing what? Y0, this is u exact, this is u evaluated, u exact, y at first node, and in this way it is better to understand the problem. And then we'll be doing what? We will be transferring our data onto the Excel so that the problem can be seen or it can be viewed graphically as well, that whether we are getting the same answer which was expected or not. So this is your challenge, friend. In this particular video, I have shown you a simple problem. I have also given you the strategy for solving this particular problem. And the task is very simple: to develop a class known as channel flow for this particular problem, having these many data members and these as your member function. And once you create an instance of this class, that is channel flow, your and then call the boundary conditions or solve function and this, and then you should get some result, and your analytical results should match the numerical result. So let us meet in the next lecture, and I hope that till the next lecture you should be in a position to solve it. At least try this problem, because this problem will make you understand the real feeling of numerical computations when it comes to programming. So in this lecture, till this point only, thank you very much. We'll meet you in the next lecture.